Welcome back, everybody. In this video, we're going to continue our discussion of infinite series, and in particular, we're going to talk about convergence tests. So likely in your Calculus 2 course, you've seen a whole plethora of them. So this is hopefully going to be a bit of a review for you. We're just going to highlight some of the convergence tests that are out there. Now, the first one we'll write down, that one shouldn't have been in your Calc 2 class, or likely was not. And this is what we're going to call the Cauchy criterion for series. This is really the same as the Cauchy criterion for sequences, only applied in the case of series. So let's start with this theorem. Again, we'll call this the Cauchy criterion for series. And what this is going to do is ask us whether or not a sequence subverges, which remember that means that the sum sequence or the series converges. And without having to know what it converges to, we can determine it if we look at the sum sequence and determine whether or not it is a Cauchy sequence. So the statement is that a sequence, and let's call it, say, A dot of real numbers, subverges if and only if, okay, so this is bidirectional, if and only if the sum sequence is a Cauchy sequence. Okay, and you'll remember when we did the Cauchy criterion for sequences, we just said that a sequence converged if and only if it was a Cauchy sequence. So here we're basically saying that the sum sequence converges if and only if the sum sequence is a Cauchy sequence, which is nothing new. It's a sequence, right? It converges if and only if it's Cauchy. Okay. The reason I write it down is because a lot of times students say, well, that's sequences and these are series, right? And how do I know that I can move from sequences to series? And of course, the answer is sequences and series are connected by series being some sequences, right? Or at least the limits of some sequences. Okay, so there's no proof here to write down. It really is just applying the Cauchy criterion for sequences in the context of some sequences. Now, we're not going to prove it, but let's explain this a little bit, right? Let's go a little bit deeper into what implication this has. So if we're talking about a Cauchy sequence, right, then we're looking at the 2D difference of the sequence with itself. And in this case, the 2D difference of the sum sequence with itself. So we're looking at the sum sequence, right, and then we're taking this 2D difference. Remember, this just means all things of this form, you'll have a1 plus a2 dot 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 plus say an, and you're going to subtract a1 plus a2 plus dot 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 plus say maybe some a sub m. Okay, so that's what things in this 2D difference look like. Okay. Now let's handle a special case, right? Let's say we're in the case where n is at least m. So if n is at least m, you're going to get a lot of cancellation here, right? The a1, the a1, the a2, and the a2, and so forth. And at some point, because n is at least m, you're going to get rid of all of the terms on the right, and maybe there's some leftover terms. So the only thing that you're going to get left is going to be a m plus 1 through an. Okay, you get rid of the first m terms, and then you get whatever is left. Of course, it could be that n is less than m. Then what would you get? In that case, well, you're getting rid of all of the a1s through an's, and then there's going to be some left over, but you're subtracting them. So you'll have a negative a n plus 1 through am. And so you can see that all of the terms in this 2D difference are going to look like sums of consecutive terms in the sequence, but maybe you're cutting off the head as well as a tail, all right? And you're just left with something in the middle, some portion of this, the sequence all added together. And of course, there could be a negative in front, right? So you're going to get on both sides of 0. Of course, if we take the absolute value, then we don't have to worry about this negative here. Okay, now, what does it mean then if this is this 2D difference, right? Or what does it mean if the sum sequence is a Cauchy sequence? It means that this 2D difference has a tail, right? It has a tail which is contained in a certain coin, okay? In fact, a 0 coin. So you choose a 0 coin, and I can find a tail that will be contained in it. Okay, so if we write that down explicitly, okay, I want to build a 0 coin, so I'm going to choose some positive real number epsilon. Then I can find a tail. So to get a tail, then I'm going to get some natural number that depends on this epsilon. Okay, so some positive integer n, such that if I have, and let me just, for sake of argument here, assume that n is at least m, and they're all going to be at least n of epsilon, then, well, the things in the tail, right, well, these are all the things, right, look like this difference, which resorts, comes down to here. You would have am plus 1 plus ... plus an, and that's going to lie in the 0 coin of radius epsilon, which is just negative epsilon to epsilon. Okay, and of course, if I looked at the case where n was less than m, then, so if n is less than m, and they're still, of course, both greater than or equal to n of epsilon, I would have negative an plus 1 plus ... plus am. This would also be in here. Okay. Really, I don't have to look at both of them, okay? Because if one of them is in this coin, then the absolute value, or the opposite of it, will also be in this coin because it's symmetric about the origin. So I really don't have to write both of them, okay? But I'm going to say it. So that's what we're really saying. If we want to see that the sum sequence is a Cauchy sequence, then we simply need that all of these guys are in this 0 coin for any epsilon, right? Or if we want to kind of put it all together into one, we could put absolute values, right? We say any expression of this form is going to have absolute value less than epsilon. Okay, so this is what this being Cauchy means. Okay, so all such expressions have absolute value less than epsilon as long as you go into a tail, right? If you go out far enough. Okay. All right, so that can be some useful bit there. Okay, let's do another test. This is probably the most important one because you can rule out convergence very, very quickly with this one. So this has a lot of names in the literature. Sometimes it's called the divergence test. For series, I call it the non-vanishing sequence test. Okay, what it's going to say is that if I have a sequence and it doesn't converge to 0, then the corresponding sum sequence will diverge. Okay? So if a dot converges to some L, which is not 0, or if A diverges, okay, so that's the two ways that a sequence could converge, or wouldn't converge to 0, rather, right? You could either converge to something else, or you could just diverge. Okay, so if either one of those happens, then A dot disumverges. Yep. Yeah, so you could write this down in the contrapositive way, right? So you could say, well, if A dot subverges, then A dot converges to 0. Okay, so that's the shorter version, right? That's the shorter version, but it's not necessarily the best version, right? It's not the one we're going to use the most. So as an example, let's say I look at the sequence A equals 1 minus 1 over n. So as n goes to infinity, we know that 1 over n goes to 0. And so 1 minus 1 over n is going to converge to 1. But because A converges to 1, and 1 does not equal 0, this immediately implies, by the non-vanishing sequence test, that A dot die subverges. Okay, so the sum sequence or the corresponding series all diverge. Okay. So this is very handy, and this is the direction that we're typically going to employ it, right? Either we know A dot diverges, or we know that A dot converges to something other than 0. Okay, next one. This is a very specific type of test. That is, you're looking at a specific type of series. So in order to write it down, let's first do a definition. So let's let R be a real number. So I can write down a sequence based on this real number. And the sequence, I'm going to put the dot, which normally should be at the bottom, I'm going to put that up top. And you'll see why in a second here. All the terms in the sequence are going to be R raised to a power. Okay, so the index that we would normally need, A sub 1, A sub 2, etc., we actually have in the exponent. The only thing that's a little bit different here is we will typically start the indexing at 0 rather than at 1. Okay, but of course, the non-negative integers are in bijection to the positive integers, and so that's okay for the purposes of sequences. Okay, so this is going to be all things, right? Looks like 1, r squared, r cubed, r to the 4th, etc. Okay, and this is going to be called a geometric sequence with ratio r. Okay, so that's our ratio r there. And of course, as soon as we write down a sequence, we get a corresponding sum sequence. Okay, and so you could have the sum sequence, and that would be the geometric sum sequence. And again, with radius r, I won't copy that. Or you might have the series that we write down, right? And this would be called a geometric series. Okay, which would be the limit of the geometric sum sequence if we knew that it actually existed. Okay, and that's going to, whether it exists or not, is going to come from our next theorem. Okay, and so this is what's sometimes called the geometric series test, but I'm going to toss in sequence here because we'll mention that as well. So sequence and series tests. All right, so there's two things to talk about here. There's the sequences and there's the series. Okay, and let's break it up. For sequences, if this R is between -1 and 1, and now here's the interesting thing, I get to include 1. And if you've seen the geometric series test before, that including 1 there might seem a little bit odd, all right? But you'll see in a second, it really is supposed to be there. However, it is going to act a little differently than all the other numbers in that interval. So if R is between -1 and 1, including 1, then the geometric sequence, R dot, converges. And whether it converges to 0 or 1 depends on which of the R's we choose. So if R is in -1 to 1, not including 1, then R dot converges to 0. Okay, well, what if it's equal to 1? Well, that's easy. You get 1, 1, 1 squared, 1 cubed, 1/4. It's the constant sequence. So if R rather equals 1, then R dot converges to 1. It is just the constant sequence. Okay, now what if we're talking about the series or the sum sequences? Well, there we see immediately when R is equal to 1, the sequence converges to 1. But if the sequence converges to 1, then the sequence does not converge to 0. And if the sequence does not converge to 0, then the sum sequence is going to diverge, right? Or R dot will die subverge. So we don't need to worry about what happens at 1. We already know. So the only possibility is actually going to be between -1 and 1. And actually, I should probably say for the sequences, otherwise, if r is not in there, so otherwise r dot diverges. Okay, so if you're outside of this interval, -1 to 1, r dot will diverge. So we also know that that if r dot diverges, then r dot disumverges. So we don't have to check anything other than this interval. And in fact, in this case, then r dot sumverges. And in fact, we know exactly what it will sumverge to, namely 1 over 1 minus r. Okay, so we can give a proof of this. So we already know, let's see, let's check the sequence stuff first, right? So if I have an r whose absolute value is greater than 1, then when I take powers of that, I'm going to get, say, absolute value of r to the n. This is going to be the same thing as the absolute value of r to the n minus 1 times the absolute value of r. And since the absolute value of r is greater than 1, I know the product is going to be greater than the absolute value of r to the n minus 1. So this is definitely an increasing sequence. All right. Now, what do we suspect it's increasing to? Is it, could it be bounded, for example? Well, let's say it was bounded, right? So if the absolute value of r to the n is, say, less than some m for all n greater than or equal to 0, then, well, what can we do? All right, we're going to try to build some sort of contradiction because we actually think this thing is going to blow up. So we play this trick. Let's take the natural logarithm of both sides. And since the natural logarithm, let's just draw the picture really quickly, the natural logarithm is an increasing function, that tells us that when I take the natural logarithm, it's not going to change the order of the inequality. Smaller inputs will lead to smaller outputs, right? So if I take a smaller input, I get a smaller output, right? This guy is less than that guy. Okay, so if I take the natural log of both sides, I get the natural log, the absolute value of r to the n is less than the natural log of m. Now, you could object at this point, well, yeah, but how do you, take the natural log if it's negative or 0? Well, remember, the absolute value of r here is assumed to be greater than 1. So this input is certainly going to be positive. All right, now I can use the log properties to pull this n to the front. So I get n times the natural log of the absolute value of r is less than the natural log of m. And so if I then divide, I get n is less than the natural log of m over the natural log of the absolute value of r. And again, you may say, wait, hold on. You just divided across an inequality. What if you're dividing by a negative number, right? That's certainly possible, right? When we write down the natural log function, there are negative values. But where does the natural log actually become positive? Well, it's after x equals 1. And we're only putting in inputs which are greater than 1. Okay, so I'm not worried about changing the inequality here. Okay, but this would now say, right, all of this here is happening for all n greater than or equal to 0. But the natural log of m is some fixed positive number. The natural log of the absolute value of r is some fixed positive number, right? So this is just some fixed real number. And this is saying then that this inequality holds for every positive integer. That is, every positive integer is less than this fixed number. And that violates the Archimedean principle. Okay, so violating the Archimedean principle. Okay, so this would be a contradiction. Okay, the contradiction comes from assuming that this r to the n is bounded by some m. Okay, so it's unbounded. And it's increasing. It's going off to infinity. All right, so it diverges in that case. Okay, so this r dot diverges. Okay, well, what if it's in between -1 and 1? Okay, well, we've already handled this case, right? If r dot is just equal to the sequence 1, because r is equal to 1, then, of course, r converges to the number 1. Fine, so let's look at the case where the absolute value of r is less than 1. All right, so if the absolute value of r is less than 1, well, we can play this exact same game that we played up here, only now when this is less than 1, this inequality will be a less than instead of a greater than. So then the absolute value of r to the n is less than the absolute value of r to the n minus 1. And of course, it's bounded from below by 0, which means we get a decreasing sequence. Okay? So we have a decreasing sequence, and it's bounded from below by 0. So by the monotone convergence theorem, we know that this actually converges. So by monotone convergence theorem, r dot converges. Oops, converges. All right, now the claim is that it's actually going to converge to 0. So let's see why that's going to be true. Well, if r is equal to 0, then this is pretty obvious, right? So if r equals 0, then r dot, which is just equal to the 0 sequence, it's constant, that definitely converges to 0. So we can assume that the absolute value of r is positive, but less than 1 still. All right, now, if we want to show that the sequence r converges to 0, then we need to show that every 0 coin contains a tail. Okay, so let's get a 0 coin, right? So we need an epsilon. So we let epsilon be greater than 0, and we want to go out far enough, right? So we need to choose some exponent so that if we go out that far, then the absolute value of r is going to be less than epsilon. Okay, so when is this going to happen? This is what we want. Oops. We want the absolute value of r to the n, for some n, we don't know what it is, to be less than epsilon. Okay, this is what we want. Well, let's take the natural log, right? Worked before. And I can pull the n down just as I did before. Okay, again, because r does not have absolute value 0, it makes sense to take this natural log. And this will be less than the natural log of epsilon. Okay, this is equivalent, okay, as this original statement was. This is equivalent to, well, I want to divide. And when I divide, I get natural log of epsilon over the natural log of the absolute value of r. But now, unlike before, where when we divided, we did not have to worry about changing the inequality, here we do. Because the absolute value of r is less than 1, I'm taking the natural log of a number between 0 and 1. This is a negative number. So when I divide by it, I don't have to worry about changing the inequality. It is a certainty that I'm changing the inequality. So this becomes a greater than. But what this tells me is that all I have to do is make my n greater than whatever this fixed real number is. And if I do that, then the terms in the geometric series will be less than epsilon in absolute value. Okay, so that's the kind of the scratch work here. All right, so now let's put it back together. Set n, which is really n of epsilon, right? It depends on the epsilon we choose, equal to the smallest, it doesn't have to be the smallest, but it's a choice, the smallest positive integer greater than the natural log of epsilon over the natural log of the absolute value of r. And now we can say if n is at least big N, then the absolute value of r raised to the nth power is less than epsilon, which implies that the zero coin, negative epsilon, epsilon, contains the tail r greater than or equal to n. Okay, thus r dot converges to 0. Okay, so that is our proof for the sequence portion of the geometric sequence test. Okay. Okay, now what do we do when we get to series? Okay, so now for series, so remember now we're only looking at r's between -1 and 1 because those are the only ones that will have a chance. Okay, and we're probably we could have written this up here, right? So otherwise, r dot disumverges. Okay. So what we're going to do is play a classic game. Okay. So r is in here, or equivalently, the absolute value of r is less than 1, whatever we like. What I want to do is set g sub n equal to a partial sum. Okay, this is one of the terms of the sum sequence for r. So this is going to be the one where I add up all of the powers of r, starting from r to the 0 and stopping at r to the n. Okay, and now here is the cleverness. Consider the expression 1 minus r times g sub n. So first, this is 1 times gn, which I can just copy. 1 plus r squared plus dot 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 plus r to the n. However, there's now a minus r, right? And r times g to the n is going to be, well, let's see, we have a minus here. R times 1 is r times r is r squared, r times r squared would be r cubed, right? That would be the next one, and you'd keep going. R times r to the n minus 1 is r to the n, and r times r to the n is r to the n plus 1. And when I subtract, all of the terms in the middle cancel, right? They're all going away, and the only thing I'm left with is 1 plus r to the n plus 1. Okay? Okay, well, where does that get us, right? Well, let's recopy this now, right? So 1 minus r gn is equal to 1 plus r to the n plus 1. Okay, and now if I divide by 1 minus r, which makes sense because r does not equal 1. Okay, 1 is not in this interval, so this is not 0. G sub n is 1 plus r to the n plus 1 over 1 minus r. And now, as n goes to infinity, we've already seen that r to the n plus 1 is going to go to 0 as long as r is in exactly this domain. So this bit goes to 0. And the rest of it is just a constant. And so in total, this is going to get to 1 over 1 minus r. But again, g sub n, right? This is just the nth term in the sequence r dot, or sum of r dot, right? This is part of the sum sequence. So this tells you that the sum sequence, right, is going to converge to 1 over 1 minus r, or if you prefer, the series starting at 0, r to the n, is equal to 1 over 1 minus r. Okay. Well, I think that's enough for this video. We'll do another video where we go through some more convergence tests. We'll see you next time.